July 22, 1962, Cape Canaveral, Florida. A rocket is climbing off the pad, engine screaming, carrying with it the first spacecraft in history built to fly past another planet. 90 seconds in, something goes wrong. The rocket begins to drift off its intended path, nosing left when it should be going straight. Down at the range safety console, an officer watches the trajectory plot bend away from where it's supposed to be. He has one job right now, and it is the worst job in the building. If this rocket keeps veering, it could come down on a shipping lane, or worse, on a populated stretch of coastline near Cape Canaveral, or even further up the eastern seaboard. He makes the call, he flips the switch, and 293 seconds after liftoff, the rocket is torn apart in the sky, along with the $200 million spacecraft riding on top of it, gone in a fireball over the Atlantic, scattering wreckage across miles of open water. The mission was called Mariner 1. Its job was to fly to Venus, humanity's first real attempt to send a machine to another world and report back what it found there. And somewhere in the debris falling into the ocean was the answer to a question that would embarrass an entire generation of engineers. Because Mariner 1 wasn't destroyed by a faulty engine, or a fuel leak, or some catastrophic structural failure in the rocket itself. It was destroyed by a mistake so small that for years afterward, people couldn't even agree on exactly what to call it. A missing symbol. A single stroke of punctuation left out of a page of equations, buried somewhere deep in the guidance software of an Atlas-Agena rocket. How does something that small bring down something that big? And how does a mistake like that survive every check, every review, every rehearsal, all the way to launch day, only to reveal itself in the worst possible moment? To understand how this happened, you have to understand what Mariner 1 actually was, and why it was flying at all. This was the height of the space race. The Soviet Union had already put a satellite into orbit with Sputnik, then a dog, then a man, Yuri Gagarin, circling the Earth while the American public watched, embarrassed and anxious, wondering if their own country's space program could ever catch up. NASA, barely 3 years old as an agency at this point, needed wins, and it needed them in front of a public and a Congress that was watching every single launch like a scoreboard. Every failure was front-page news dissected in editorials about American decline. Every success bought the agency a little more room to breathe and a little more funding for what came next. The pressure on every engineer working these programs wasn't abstract. It was measured in headlines. Venus was the obvious next target. It's the closest planet to Earth, closer even than Mars in terms of orbital distance at certain points, and it's wrapped in a thick, permanent blanket of cloud that no telescope on the ground could see through, no matter how powerful. Nobody knew what was underneath those clouds. Some scientists, working off decades of speculation and a handful of ambiguous spectroscopic readings taken from Earth-based observatories, thought Venus might be a lush, humid, swampy world, maybe even something approaching habitable, a twin of early Earth shrouded in mist. Others, looking at how close Venus sits to the sun and how thick its atmosphere appeared to be from what little could be measured, suspected it was closer to a furnace, a planet where any ocean would have boiled away eons ago, leaving behind something closer to a pressure cooker. Nobody could resolve the argument from Earth, no matter how good the telescope. The only way to actually find out was to send a machine there and let it look for itself, up close, with instruments no telescope could match. So NASA built two identical spacecraft, Mariner 1 and Mariner 2, designed to launch back-to-back within about a month of each other. This wasn't a backup plan born purely out of caution. It was standard procedure for the era, because in this early period of spaceflight, spacecraft failed constantly. Depending on how you count it, something like half of all planetary and lunar missions attempted worldwide up to that point had ended in failure of some kind, whether that meant a launch vehicle explosion, a guidance failure, or a spacecraft simply going silent partway through its journey. Having a second, identical spacecraft ready to go wasn't a luxury bolted on for peace of mind. It was closer to a working assumption baked into the entire program. Mariner 1 would go first. If it worked, Mariner 2 would follow and expand on the science. If it didn't, Mariner 2 would carry the entire mission on its own shoulders, and the engineers all knew it. Now, getting a spacecraft to Venus is nothing like pointing a rifle and pulling the trigger. Venus doesn't sit still, and neither does Earth. Both planets are moving around the Sun at completely different speeds, on different orbital paths, at different distances from the Sun. A spacecraft has to be launched at exactly the right moment, in a narrow window that only opens up every so often, on exactly the right trajectory. Aim not at where Venus is on launch day, but at a point in space where Venus will be months later, after both planets have continued their separate journeys around the Sun. This kind of targeting requires a rocket that flies an extremely precise path in the first few critical minutes of flight, because any small error introduced at the very start of the journey compounds enormously by the time you're talking about a voyage of many tens of millions of kilometers through open space. A guidance error of a fraction of a degree at launch can translate into missing your target by a margin of thousands of kilometers months later, more than enough to turn a historic flyby into a wasted mission, sailing uselessly past an empty patch of space. That precision was the job of the Atlas-Agena rocket's guidance system, and specifically, a ground-based radar tracking setup working hand in hand with a computer on the ground. Here's how the system was designed to work, step by step. As the rocket climbed off the pad and arced out over the Atlantic, a radar antenna on the ground would track its exact position and velocity in real time, painting the rocket dozens of times per second, building up a continuous picture of exactly where it was and how fast it was moving in 3 dimensions. That tracking data was fed continuously into a computer on the ground, which compared where the rocket actually was against where it was supposed to be, according to a pre-programmed, idealized trajectory calculated in advance by mission planners weeks earlier. If there was any discrepancy between the two, the ground computer would calculate a correction, and that correction would be radioed back up to the rocket in flight, telling its engines to nudge this way or that way to steer it back onto the planned course. This is what engineers call a closed loop. Ground radar watches the rocket, a computer does the math, and the rocket obeys the correction over and over, dozens of times a second, all the way through ascent, until the rocket reaches the point where it can fly the rest of the way on inertial guidance alone. It only works, though, if every single piece of that loop is telling the truth about what's actually happening in real time. On the day of the launch, the radar tracking briefly dropped out for a fraction of a second. This kind of momentary signal loss wasn't unheard of. Radio and radar systems in that era, and honestly, even with modern technology, occasionally experience brief interruptions from atmospheric interference, hardware quirks, or simple signal noise bouncing off the wrong surface at the wrong angle. And the system was specifically designed to handle exactly this scenario, because the engineers who built it knew radar dropouts would happen eventually, probably during some launch, and they didn't want a routine survivable glitch to become a mission-ending event. If the radar signal became noisy or cut out for a moment, the onboard guidance software was supposed to smooth over that gap using a mathematical technique borrowed from control theory, essentially bridging the missing data rather than reacting to it. The software would take the rocket's last known velocity and use it to predict or interpolate the rocket's position during that brief gap, filling in the missing data with a calculated estimate rather than treating the interruption itself as evidence that the rocket had suddenly gone haywire. This is completely normal engineering practice then and now. Engineers write these smoothing or interpolation routines specifically because sensors are never perfectly reliable, and a guidance system that panics and overreacts every single time it loses a signal for half a second is a guidance system that will tear itself apart at the very first minor hiccup of any flight, radar dropout or not. But something in that particular guidance equation, the one responsible for smoothing over exactly this kind of radar dropout, was wrong. Instead of gracefully bridging the gap the way it was supposed to, the software began interpreting completely normal, expected fluctuations in the rocket's velocity as genuine errors that needed correcting. And because the underlying formula itself was flawed, not corrupted, not glitching randomly, but mathematically wrong in a specific and repeatable way, every tiny natural variation in the rocket's actual flight, the kind of minor wobble every rocket experiences constantly due to atmospheric buffeting, engine vibration, and fuel sloshing inside the tanks, got treated by the software as a real deviation, demanding an aggressive steering correction. The guidance system began commanding the rocket to make sharp, entirely unnecessary steering maneuvers to fix a problem that did not actually exist anywhere except inside its own flawed math. It was chasing noise, treating the rocket's own natural jitter as if it were drifting dangerously off course toward disaster. And here's where it gets worse. The harder the system tried to correct for these imaginary errors, the more it actually knocked the rocket off its real, intended trajectory, which then in turn triggered even bigger corrective commands, because now there was a genuine and growing deviation for the flawed equation to latch onto and amplify even further. It was a feedback loop spiraling in exactly the wrong direction, feeding on its own mistakes, compounding with every fraction of a second that passed, and it all happened within seconds of that momentary radar handoff. Think of it like a driver overcorrecting on an icy road. A small skid triggers a jerk of the wheel one way, which triggers a bigger jerk the other way to compensate, and within a few seconds, what started as a barely noticeable slide has become a full, uncontrollable spin. Except here, the driver was a computer executing a flawed equation with total mathematical confidence and zero hesitation, dozens of times per second, incapable of stepping back and asking whether any of this actually made sense. The range safety officer watching the trajectory plot didn't know any of this yet, of course. All he could see, in real time, was a rocket that was no longer flying where it was supposed to be, and getting worse by the second, with no sign of self-correcting, no sign of stabilizing. Standard procedure in a situation like this, when a rocket becomes unpredictable this early in flight, this close to a populated coastline, is to destroy it deliberately before it can do something far more dangerous entirely on its own, coming down somewhere far more catastrophic than open ocean. So he sent the destruct command, and Mariner 1 never got the chance to reach orbit, let alone Venus, let alone answer any of the questions it had spent years and millions of dollars being built to ask. In the aftermath, NASA convened an investigation board, and its engineers went hunting through the guidance software line by line, trying to find what could possibly have caused a routine smoothing algorithm to behave so violently and so specifically wrong under just this one set of conditions. And what they eventually found was, on paper, almost comically small for the scale of destruction it had caused. Somewhere in the process of translating the guidance equations from their original handwritten mathematical notation into the actual code that ran on the ground-based guidance computer, a single symbol had been dropped. In the original formula used by the engineers who designed the guidance logic, a small mark, commonly described in later retellings as a superscript bar or overline, used in mathematical notation to indicate a smoothed or averaged value over time, had simply not made it into the final implemented version of the equation. Without that one symbol, the equation the software was actually executing described something subtly, but critically, different from what the original engineers had intended on paper. Instead of properly smoothing the incoming velocity data the way the math was designed to, the equation as coded was mathematically primed to treat ordinary, expected variation in that data as a real and urgent deviation, demanding immediate correction every single time, with no way to tell the difference between real drift and normal noise. This is the part of the story that's genuinely hard to wrap your head around. This wasn't a typo sitting in a comment somewhere, or a mislabeled variable, or a value that was simply off by a decimal point. The kind of thing you could squint at a printout and immediately catch on a second read. This was one tiny piece of mathematical notation, present and correct in the original derivation on paper, missing in the version that actually got implemented as running code, and the absence of that single mark changed the entire behavior of the guidance logic, but only under one very specific condition: a brief radar dropout, which just so happened to occur during this particular launch. Run the exact same rocket with the exact same flawed code without that momentary radar interruption ever happening, and the flaw might never have surfaced at all, might have flown perfectly and been quietly buried in the software for the next mission too. It had probably been sitting dormant in that formula for weeks, maybe months, through simulations, through ground tests, completely invisible the entire time, simply waiting for the one specific real-world condition that would finally expose it in the least forgiving way possible. So how does something like this get past every level of review? Part of the answer lies in just how dense these guidance equations really are. They're full of nested calculations, smoothing terms, correction factors, feedback gains, all expressed in a mathematical shorthand that is difficult enough to read correctly in the first place, let alone verify symbol by symbol against a handwritten specification drawn up separately by someone else on a different desk, possibly weeks earlier. And remember, this was 1962. This was an era before automated software testing, before version control systems, before the kind of exhaustive simulation environments that exist today, where engineers can run thousands of virtual flights and deliberately inject artificial sensor faults to see exactly what breaks and why. Verifying software in 1962 often came down to engineers physically reading printed listings of code and comparing them, line by line, symbol by symbol, against handwritten formulas on paper, a process that is exactly as fallible, exactly as prone to simple human oversight as it sounds when you say it out loud. Nobody involved was being deliberately careless or cutting corners to save time. This was simply an extraordinarily easy mistake to make under real deadline pressure in a program racing against a geopolitical rival, and an extraordinarily difficult one to catch, precisely because it only manifested under a rare and specific trigger condition that most routine testing scenarios never happen to reproduce. There's a broader lesson buried inside all of this, and it's one this channel keeps circling back to, again and again, across completely different fields of engineering, whether we're talking about helicopters on Mars or bit flips inside a supercomputer. The systems we build to control genuinely powerful things, rockets, aircraft, nuclear reactors, are often only as trustworthy as the smallest, most easily overlooked detail hidden somewhere inside them. And the people responsible for catching those details are exactly as fallible as anyone else, working under real deadlines, under real pressure, translating elegant mathematics into code that a machine will then execute completely literally, with zero judgment, zero common sense, and zero ability to notice when something looks slightly off compared to what was intended. A computer doesn't know what you meant to write. It only knows exactly what you actually told it, symbol for symbol, and it will follow that instruction with perfect, unwavering obedience, straight into a feedback spiral, if that's mathematically what the equation says to do, with no hesitation and no second thoughts, which is exactly the kind of small, invisible risk you don't want quietly hiding somewhere in your own digital life either. Today's sponsor name, works a little bit like the review process NASA wishes it had back in 1962, except this time it's watching over your personal data instead of a rocket's guidance code. Sponsor name scans the web for the places your personal information, your name, Your home address, your phone number, has quietly ended up without your permission, sitting inside data broker databases that get bought and sold constantly, often without you ever finding out it happened. Then it automatically files removal requests on your behalf, the kind of tedious, repetitive checking that would otherwise take you dozens of hours to do by hand, exactly the kind of task where a single misstep lets something slip through unnoticed for years. If you want to see where your own data has quietly ended up, head to sponsor link and use code for a discount on an annual plan. Thanks to sponsor name for supporting this video. Now back to 1962. The failure of Mariner 1 could very easily have ended the Venus mission entirely, could have set the entire planetary exploration program back by years, and could have handed the Soviet Union an even bigger propaganda victory at the height of Cold War tension. One more headline about American failure in the space arena. Instead, NASA had built in exactly the kind of redundancy this story would go on to prove the value of, decisively and immediately. Just over a month later, on August 27, 1962, Mariner 2 lifted off from that same launch pad at Cape Canaveral, carrying corrected guidance software, the missing symbol finally restored, the flawed equation fixed after engineers traced the failure all the way back to its root cause, symbol by symbol, line by line. This time, the rocket flew true. No wild oscillations, no runaway feedback loop, no destruct command from a nervous safety officer. Mariner 2 climbed cleanly into its trajectory and went on to become the first spacecraft in human history to successfully fly past another planet, sweeping within roughly 35,000 kilometers of Venus in December of 1962, and radioing back data that gave humanity its very first real scientific look at another world up close. After decades of pure speculation, what it found settled the argument that had been raging among scientists for decades. Venus wasn't a humid paradise, wasn't some tropical twin of early Earth hiding beneath its clouds waiting to be discovered. It was scorching, with surface temperatures reaching far beyond anything that could support liquid water, let alone the lush oceans some scientists had hoped for. One mission's total failure and its successor's historic success happened only about 5 weeks apart, separated by nothing more than one restored piece of mathematical notation and the engineers who finally tracked it down under enormous pressure, working around the clock to make the next launch window. The Mariner 1 incident became something close to a foundational case study in the field that would eventually come to be called software engineering. A discipline that, in 1962, barely had a name yet, let alone textbooks, standardized practices, or a professional body overseeing it the way it does today. It's frequently cited, sometimes with the details blurred, simplified, or exaggerated over 60-plus years of retelling, as one of the earliest and, adjusted for the era, most expensive software bugs in recorded history. And whatever the exact version of the story you encounter, told slightly differently in different textbooks and documentaries, the core truth underneath it all holds up under scrutiny. An entire spacecraft, an entire mission, tens of millions of dollars in 1962 money, undone by a single symbol that a person forgot to write down while translating a formula from a page of handwritten mathematics into a machine that would execute it without question, without judgment, and without mercy. In the decades since, this story has become something close to folklore in engineering circles, repeated over and over anytime someone wants to make the point that in sufficiently complex systems, the smallest, most invisible details carry the largest possible consequences. Aerospace software review processes today are almost unrecognizably more rigorous than anything that existed in 1962, layered with redundant independent checks, automated static analysis tools that can flag inconsistencies a human eye would miss entirely, and dedicated simulation environments built specifically to inject rare condition faults, radar dropouts, sensor glitches, timing errors, and see exactly how the software responds before any of it is ever allowed anywhere near a real launch pad with a real spacecraft sitting on top. In a very real sense, every additional layer of testing bolted onto spacecraft software in the years since exists because engineers learned the hard way in front of the whole world in a watching Congress that a formula which looks correct on paper is not remotely the same thing as a formula that has been proven correct once it's translated into running, executing code. Somewhere off the coast of Florida, the scattered pieces of Mariner 1 still rest on the ocean floor, a spacecraft that never got the chance to lay eyes on the planet it was built at enormous cost to visit. But buried inside the wreckage of that failure was the blueprint, quite literally, for how to get it right the very next time, only weeks later, under the exact same time pressure that had helped create the mistake in the first place. Mariner 2 flew, and flew successfully, because Mariner 1 fell, and because somewhere in a room full of engineers working against the clock, against a launch window that wouldn't wait, someone finally found the one mark that had been missing all along. Thanks for watching.